In section 21.5, talking about detecting radiation, we're only going to be looking at one little sliver of information about PET scans. And the word PET scan stands for positron emission tomography scans. So positron emission tomography, and the way that it works is that you have a patient that you need to scan something, usually in the brain, but it can be somewhere else. They inject them with a positron emitter, and so they'll inject that. That positron emitter is radioactive. It will go to certain parts of either the brain or other organs, and it tends to be, typically they'll inject something that's a labeled radioactive glucose. And in doing that, that glucose goes to places where lots of energy is being used, like where cell reproduction is occurring, and it causes that to light up on the positron emission tomography analysis. Now, when this happens, what they're actually looking at is not the positrons themselves. It's that the positrons, as you may or may not remember, positrons react with electrons to give gamma rays. And so what you're actually detecting are the gamma rays. So as soon as the positron and the electron run into each other, they'll give two gamma rays. Those two gamma rays go in opposite directions, and then those will be detected by these scintillation counters. And so there's lots and lots in this array, and then you scan different slices, and you're able to observe what brain structures look like. And so you can look for things like damage to the brain, but you can also look for things like tumors. And so PET scans are a very powerful tool for imaging certain parts of the body, and in particular the brain, which is a very sensitive part of the body. Hopefully you'll never need one, but if you do, you'll be glad that it exists. It has saved a lot of lives by being used. All right, so we're now going to look at the topic of energy in nuclear reactions. This is a long section. There's a lot to this section, so we're going to take our time going through it. You will learn a lot in this section. So I'm going to start by showing you an example to illustrate what this section is all about. So we're going to start with the alpha decay of uranium-238. So uranium-238 gives us thorium-234 plus helium. And we'll see that the numbers add up. 238 is equal to 234 plus 4, and 92 is equal to 90 plus 2. And so you would think, okay, well, we should have exactly the same amount of mass before and after the reaction. That's what Antoine Lavoisier told us. That's what we should expect. And if we measure it, it's almost true. So if we look at the mass of uranium-238, the atomic mass of uranium-238, we'll get this number, 238.050788. That number in and of itself is not too important, other than we're going to take the difference. And you'll see, 238 plus 2 is 234 plus 4. It looks like it balances, right? But when you look real close and you go out to more significant figures, you'll find that this doesn't quite add up, that we can get a change in mass. So we'll do the mass of the products minus the mass of the reactants, and we'll get this. Now, I'm doing this per mole. This is AMU, and we're doing this per mole. And so we're going to get, we'll take the number 234.043601 grams, this many grams, that many grams, and that's going to give us our answer per mole instead of per atom. But that said, that's how many gram difference is going to be. And when we do the math, this is the number we get. The mass of our products is 0.004584 grams less than the mass of our reactants. So that means that the mass disappears. That would appear to violate the law of conservation of mass. but it doesn't. What's actually happening is that mass is getting converted into energy relativistically. So what that means is our conversion factor for this is going to be Einstein's equation, E equals mc squared. So what this means is that we need to combine the law of conservation of mass and the law of conservation of energy, because it's possible that mass, in a way, can get converted into energy. It's also technically possible that energy can get converted into mass, but that's a harder thing to do. So let's calculate the energy change. We've calculated the change in mass. Let's calculate the energy change. So there are the numbers that we started with, and then there is the change in mass in grams. We are going to put that into our equation. So delta E is equal to delta M times c squared. So c is just the speed of light. And so here is our mass in grams. We do need to convert it into kilograms. And you'll notice I have the negative there because we lost that mass. And then here, this is the speed of light. And usually when I'm doing the speed of light, I have at least as many sig figs in the speed of light as I have here. So as long as we have at least as many sig figs in the speed of light as we have here, we're okay. If you have fewer, then you're going to end up with fewer sig figs. And we have as many sig figs for the speed of light as we need to because it's an exact defined quantity. So we'll have a delta E that is equal to negative 4.120 times 10 to the negative 11 joules. And you may be wondering, okay, well, how much is that? I mean, that's 412 billion joules, 412 giga. That's a lot of energy. All right, so that's a lot of energy. So 412 billion joules. If you took my first semester of general chemistry, then you'll recognize this number. That is equal to 2.77 billion Randy Johnson fastballs. Each Randy Johnson fastball is worth about 149 joules. So you just take that number, divide by 149, you get that number. Anyway, Randy Johnson was a major league baseball pitcher, and he once threw a baseball at 102 miles per hour. And if you do the conversion, that comes out to 149 joules. And so that's how many baseballs that would be. It's a lot. It's a lot of energy. So we're going to look at numbers 44 and 50. And I'm going to warn you, number 50 is kind of long. So let's do number 44 to start with. The good thing is if you get tired while you're watching this video, you can pause the video. When you're taking this in class, that it's a little bit harder there. So an analytical balance typically measures mass to the nearest 1 milligram. So, or I'm sorry, 0.1 milligram. So that's a really nice balance. The ones that we have in our lab, they go to the nearest milligram. The ones that we use, the student balances, we have one in the back that goes to the nearest tenth of a milligram, but it's really expensive. So, okay. What energy change would accompany the loss of 0.1 milligrams of mass? So we're going to do that calculation. Delta E is equal to the delta M times c squared. So delta M is going to be equal to negative 0.1 milligrams. We'll need to convert that milligrams into grams. So there's 1,000 milligrams is equal to 1 gram. And then 1 kilogram over 1,000 grams. So that is our change in mass. And then for the speed of light, we only have one sig fig here. So I'm just 3.0 times 10 to the 8th meters per second. And this is important. We can't forget to square. If we forget to square, all bad things happen here. So, all right. So let me get this. Let's get this out a little bit. So we got plenty space. Okay. So, so we'll do negative 0.1 divided by 1,000, and then divide by 1,000 again. And then we want to multiply by 3.0 times 10 to the 8th squared. And that gives us a big long number, and I'm going to count the zeros. So 1, 2, 3, 6, 7, 8, 9. So that's going to be negative 9 times 10 to the 9 joules. So that's going to be equal to negative 9 times 10 to the 9 joules. That's 9 billion joules of energy. It's 9 billion joules of energy. That's an enormous amount of energy. So when 1/10 of a milligram gets converted into energy, 9 billion joules of energy is released. Okay, so let's look at number 50. So calculate the energy released per mole in each of the two reactions below. Then compare the energy released in the fission reaction with the fusion reaction. All right, so this is a time-consuming problem. So you just have to kind of be patient while you're setting it up. So we're going to be patient as we're doing this. Okay, so when we're setting this up, we'll do the delta M first. So delta M, it's going to be the change in mass. And so it says compare the energy released when the fission, the fusion, use the following attack. And we're doing this per mole. So we're going to take the atomic mass units and we're going to convert those. We're just going to make them grams, and that will get it per mole. So it'll be products minus reactants. So our mass of one barium is, the barium 141 is right there. So that's going to be 140.914411 plus the krypton 92, so 91. 156 plus 3 times 1.0086649. This is a very meticulous problem. And then minus, minus the reactant, so 235, so we'll do 235.043930 plus 1.0086649. Okay, so we're going to punch all those numbers in. So 140. I'm going to turn my mic off. Okay, so I did round to whatever that place is. One, 2, 3. It's whatever that place is. That's the thousandth, millionth place. All right, so I rounded to the millionth place on that. All right, so that is our change in mass. And so now we're going to put that into our equation, our delta E. And our delta E is negative 0.18 0.8633 grams, 1,000 grams, 1 kilogram. And for the speed of light, 2.9979. Here, let's just get the number there. Speed of light, 2.99792458. We'll just put the whole thing in there. So I've already forgotten it. So 2.99792458. 2458 times 10 to the 8th meters per second and squared. All right, so I'm just going to take that number that's in the calculator, divide by 1,000, and that will give us this. And then we're going to multiply that by 2.99792458 times 10 to the 8th. And that's going to give us negative 1. Let's see, we have 6 sig figs. So 1.67198 times 10 to the 13th joules. Okay, and that is the number I have on my key as well. Thank goodness. All right, and that is per mole of 235, uranium-235. Okay, so now we're going to do the same kind of calculation for this one. Again, I'm going to turn off my microphone. I'm going to turn off my microphone for a minute so you don't hear me like snorting and breathing in your ear. All right. All right, so I finished that calculation, and you'll see that we've got the, so negative 1.67, it's about 1.67 times 10 to the 13th joules for the uranium-235, but that's per mole. And then this one is 1.77 times 10 to the 12 joules per mole on this one. So this one's about an order of magnitude less than that one per mole. However, if you take this and divide, you do the joules per gram. So if you convert the moles into grams, you'll find that this one, and I'm just going to approximate here, it comes out to about 7.1 times 10 to the 10 joules per gram. Whereas this one comes out to approximately, and I've got these numbers recorded on my key, 3.5 times 10 to the 11 joules per gram. So you have a lot more energy density with the fusion. And so fusion reactions give off more energy per gram, per nucleon, if you want to think of it that way, than fission reactions. However, fission reactions, those are the ones that we are more accustomed to. So, all right, I'm going to go back to our presentation here. So we want to look at energy production in the sun, because the energy that comes from the sun is by doing these fusion reactions, like that second one we just did on number 50. So we'll find that in the sun that about 4.26 times 10 to the 9 kilograms of mass is converted into energy every single second. And it's been doing it for about 5 billion years. Now, it has varied over the 5 billion years, but the point is it's a lot of mass getting converted into energy. When you put that into Einstein's equation, what you're going to end up getting is a power output of 385 times 10 to the 24 joules per second, or 385 times 10 to the 24 watts, if we want to put it in terms of watts. And if you want to use my favorite unit of energy, that's about 2.58 times 10 to the 24 Randy Johnson fastballs per second. Or if you have one of these, that's enough power to power 2.1 times 10 to the 15th flux capacitors. And a flux capacitor, this is a flux capacitor. And if you don't know what this is, then you have been deprived of a good childhood. 2.1 times 10 to the 15th, let's see, that would be trillion, quadrillion, 2.1 quadrillion flux capacitors. And if you still have no idea what this is, you need to stop what you're doing this weekend, whatever you're doing. I want you to go and watch Back to the Future, and you'll learn all about this flux capacitor. So, okay, so enough of that. That's all kind of fun and everything. But the sun is pouring out an enormous amount of energy all the time. Now, we only absorb a tiny little sliver of that because Earth is not very big compared to the sun, and we're 150 million kilometers away from it. So we're just getting a little tiny sliver of it. But boy, on a hot day in Texas, it feels like we're getting all of it, doesn't it? Okay, so we want to talk about the next topic, and our next topic is something that we refer to as mass defect. And again, to illustrate what mass defect is, I'm going to show you how to do the calculation for carbon-12. So carbon-12 has an atomic mass of exactly 12 atomic mass units. So if you have one carbon-12 atom, it's exactly 12 atomic mass units. And if you look, that has 12 nucleons that are in carbon-12. And those 12 nucleons, there's 6 protons and 6 neutrons. So the mass of the individual nucleons, when they're not together, is going to be the mass of 6 protons plus the mass of 6 neutrons. Well, if we start doing the math, here, this is the atomic mass, so we're going to subtract the mass of 6 electrons. When we subtract the mass of those 6 electrons, so this is the mass of the 6 electrons, you'll find that on the back of your periodic table. When you subtract that, you're going to get 11.9967. It's almost 12, right? So it's not quite 12 atomic mass units for the mass of just the nucleus. Well, now let's do this. The mass of a proton is 1.0072765, and the mass of a neutron is 1.00866649. And so, I mean, you can already tell this number is going to be bigger than 12. 6 times a number bigger than 1, 6 times a number bigger than 1. We're going to have a number bigger than 12 here. That number comes out to 12.0956484 atomic mass units. And now we're going to take the difference between these two numbers. So the mass of the nucleons minus the mass of the nucleus, and that gives us what we're going to call a mass defect of 0.0989399 atomic mass units. Okay, so here's what happens. Is that when you have these 6 individual protons and neutrons, and they eventually come together to form a carbon-12 nucleus, which, by the way, they don't do all at once, but hey, it's a state function just like enthalpy and entropy. So we will find that when they combine together, that the mass of the new particle is less than the mass that we started with, and so that difference, that mass defect, is converted into energy. That energy is the amount of energy that is holding together that nucleus. We call that the binding energy. So we're going to take this number in atomic mass units and we're going to convert that into joules, and we're going to call that the binding energy. So we're going to do that on the next page. So let's do that. All right, so again, here are the numbers that we started with. There's the mass. There is our mass defect. Now we're going to convert that mass defect from AMUs into grams. So we'll take the 0.0989399 atomic mass units. We'll divide that by the Avogadro's number, 6.022140076, and I've got a ridiculous number of sig figs there, times 10 to the 23rd, and that is AMUs per gram. Again, that's Avogadro's number. So now we're in grams. And then we will divide that by 1,000 to get us to kilograms. And so this is our mass defect in kilograms, which that's hardly anything, but that's the mass defect for exactly 1 carbon-12 atom. So that's the mass defect for 1 carbon-12 atom. So now what we want to do is we want to take that number and use Einstein's equation. So delta E is equal to that mass defect, that 1.64294 times 10 to the negative 28 kilograms, multiplied by the speed of light squared, and then we get this. And this, the 1.47660 times 10 to the negative 11 joules, that is the binding energy. So that is the binding energy of one nucleus. That is the amount of energy that is holding together that nucleus. So that is the amount of energy that is holding together that nucleus. Now, that's a very small number, but for one nucleus, that's a significant number. So now what we want to do is we'll take that number. So we'll take that 1.47660. We're going to take that number. We want to get the binding energy per nucleon. So the binding energy per nucleon. So the binding energy per nucleon, this is an easy calculation. We just take that binding energy that we just calculated, the binding energy per nucleus, and we want to divide by the number of nucleons. So here we've got 6 protons and 6 neutrons. That gives us 12 nucleons. So we'll divide by the 12 nucleons. and that gives us a number of 1.23050 times 10 to the negative 12 joules per nucleon. And that is our binding energy per nucleon. Here's the thing. The bigger that number is, the more stable the nucleus. The smaller that number is, the less stable the nucleus. So that number, it doesn't seem very big, but it's bigger than some of the other numbers that we run into when we're looking at binding energies per nucleon. So, just remember 1.23 times 10 to the negative 12. We're gonna come back to that. 1.23 times 10 to the negative 12. So here are a few examples of a few example binding energies per nucleon. The binding energy per nucleon is a measure of how stable a particular isotope is. Again, the larger the binding energy per nucleon, the more stable. Here are some example binding energies per nucleon. Helium, 1.13, so that means that there's some stuff we can do with that. Iron 56, if you look at that one, iron 56, 1.41 times 10 to the negative 12. That ends up being one of the largest binding energies per nucleon. And it turns out that once you're in that range, there's not much that's going to happen to that atom. So that ends up being pretty stable. So here is the thing. And this is a quote from the textbook. The trend indicates that nuclei of intermediate mass numbers, meaning mass numbers at around 55 to 60, we'll just say, are more tightly bound and therefore more stable than those with smaller or larger mass numbers. So iron is a pretty big mass number, relatively speaking. Okay, so I'm going to show you a graph that shows the trends here. So on this graph, I went into Excel, and I'm such a nerd. I went into Excel and I entered in every single known isotope. There are approximately 265 of them. And I entered them all into a spreadsheet and calculated the binding energy per nucleon for every single isotope. Now that sounds like that would be really, really tedious, and that would be correct. It is a little bit tedious, but I really wanted this graph. I wanted a better version of this graph. So you're just going to have to trust me. This is a nice graph. Now, sorry the sizes are so small here, but here's our binding energy per nucleon, and we've got hydrogen, deuterium, helium, there's hydrogen 3. You'll see that every single one is represented, and I've labeled just a couple of the important ones. We'll find that heavier nuclei like uranium will tend to undergo fission. And what happens is it breaks apart into smaller nuclei, and by going up here in binding energy, that means it's going to be more stable. We'll find here that we've got iron 58 and nickel 62. Those are two of the most stable ones. So anything that's in there in that 55 to 65 range as far as the mass number is going to be pretty darn stable. And then you'll see down here our smaller elements, they can undergo fusion. So for example, if we've got deuterium and helium-3, they combine together to make hydrogen and helium-4. And that is one of the fusion reactions where you get a huge bump in the binding energy per nucleon when you do that, and therefore it releases an enormous amount of energy. So that's why those fusion reactions release so much energy. So fusion reactions, they emit great amounts of energy because they combine together to release some energy. So we're going to look at numbers 47 and 51 on the in-class assignment. So 47. So here, predict which of the following nuclei will have the largest binding energy per nucleon. So we've got boron 11, vanadium 51, tin 118, and curium 243. Well, we want one that's like closest to that 55 to 60 range. So the one that is going to have the largest binding energy per nucleon is going to be the vanadium out of that list. And because it is closest to the 55 to 65 range. Again, we're just looking at the mass number there. All right, we're going to calculate the binding energy per nucleon for each of these. Okay, so the key to doing this particular problem is one, don't get overwhelmed. So don't get overwhelmed. We're going to start by figuring out what it is we need to look for. We're going to find the mass defect first. So to do that, we'll need to know how many protons. Well, there are 27 protons in that nucleus. And the number of neutrons is 32 neutrons. So our mass defect is going to be the mass of the nucleons minus the mass of the nucleus. So the mass defect is going to be the mass of our nucleons, and the mass of our nucleons is going to be 27 protons plus 32 neutrons. And then we want to subtract the mass of our nucleus. Well, we were given the atomic mass. Now, in the next problem, you'll see it's given the nuclear mass. And if you're given the nuclear mass, then it's already done part of the calculation for you. So, get that just a smidge closer. Okay. So here, to get the mass of the nucleus, we'll want to take the atomic mass and subtract the 27 electrons. So we'll do 27 protons plus 32 neutrons, and we'll subtract away atomic mass minus 27 electrons. Okay, so we're going to need the quantities that are on here. So we're going to need those quantities for our electron mass and for our neutrons. All right. So again, don't get bogged down in this. So we'll do 27 times the mass of a proton, and the proton mass is 1.007275. So 1.00072765. All right, plus 32, put that together. So 32 times the mass of a neutron, which is 1.00866649. So 1.00866649. Okay, and then we're going to subtract our atomic mass, which is 58.933195 minus 27 times, and our electron mass, 5.485799, 5.485799 times 10 to the negative 4. All right, so now we are ready to do a calculation. I'm going to get that out of the way. All right, I'm going to turn my microphone off while I punch this in. Okay, so at this point we have calculated the mass defect per atom. So we've got the mass defect per atom. And so the next thing we want to do is we want to convert this into kilograms. So we want to convert it into kilograms. So we're going to need to take that number and divide by Avogadro's number. So we'll want to divide by Avogadro's number. So I'm just going to clear that out. And I'm going to turn off my microphone again. Okay, so now we've got that mass defect in kilograms, and so now we can use Einstein's equation to get the binding energy per atom. Okay, so that number that we got there, that is the binding energy per atom. So I'm going to put that right below. That's our binding energy per atom. So we now want to calculate the binding energy per nucleon. And our binding energy per nucleon, that's a pretty easy calculation. So we'll do 8.2. Again, I'm going to turn off the mic. All right, there we have calculated the binding energy per nucleon. So the binding energy per nucleon. All right, so the key difference on this next one, the key difference is that we've got the nuclear mass instead of the atomic mass. So we'll still have to do the 17 protons, and we have 20 neutrons. All right. Here, our mass defect is equal to the mass of our nucleons, which is what we did up here. We just did it 27 plus 32 there. But our mass of our nucleons minus the mass of our nucleus. All right. And since we're given the nuclear mass, that means we're ready to go. So that gives us 17 protons plus 20 neutrons. And then we're going to subtract away the mass of our nucleus. All right. So just like I did before, I'm going to turn off the microphone so you don't hear me breathing and snorting while I'm doing this calculation. All right, I had a little calculator disaster when I was working there, but here we've got our mass defect in AMU, and that is our mass defect per atom or per nucleus, if we want to think about that. That's our mass defect per atom. All right, now that we've got our mass defect per atom, we're going to do the same thing where we convert it into kilograms. And so I'm going to do just like the calculation up here, but I'm going to do it with my microphone off. Okay, so now we've got, that is our binding energy per atom. I'll go ahead and write that there. So our binding energy per atom. We've got one last little calculation to do, and I know this is a bear, but our last little calculation to do on this is going to be our binding energy per nucleon. So we'll take that 5.08053. And then our number of nucleons in this case is 37. So 37 nucleons. So I'm just going to take that number that's in my calculator and divide by 37. And we get 1.37312, it looks like, right? 1.37312 times 10 to the negative 12 joules per nucleon. And you may be wondering, why do we have so many sig figs? And that's because all of these calculations were invented by nuclear chemists, and they love having lots of sig figs. But there we go. That's our binding energy per nucleon. Not surprising, the binding energy per nucleon for the first one was bigger because that one was closer to about 60, right? It was at 50. It was at 59. It was the mass number. This one with a mass number 37, it wasn't quite as high. Okay, so that is the, let's see, that is the end of 21.6, and it's also the end of all the stuff on the in-class assignment. So I'm going to take this opportunity to stop, and we'll do the last 3 sections in a last video, and those don't have any in-class assignment, but they are quite interesting. So